Welcome back. This is the second part of lecture 5, and in this lecture we will discuss Bernoulli's equation. So the equation of the form dy by dx plus a of x into y is equal to b of x into y raised to n, some powers of y, is called an Bernoulli equation. So what makes this equation different from linear equation is that this term y raised to n, which is attached to the b of x. In linear equation, this b of x is appearing as a function of x alone. There is no y raised to n attached to this. Okay, so when n is equal to 0, definitely this is going to be a linear equation. Now to solve this Bernoulli equation, we reduce this to a linear equation by a particular substitution, and then we can solve that linear equation with the new dependent variable and find a solution for that, which in turn will give me the solution for this given equation 1. So let us try to solve this. So first what we do is that we divide this term in as a function of y that is appearing on the right hand side, both the sides. So dividing y raised to n, divide y raised to n both sides, we get 1 by y raised to n into dy by dx plus a of x y upon y raised to n, that same as y raised to n minus 1, is equal to b of x. Let me call this as equation 1. Now the substitution here is going to be this. See, when I substitute z, say new dependent variable, as 1 by y raised to n minus 1, what will happen is that this is actually same as saying y raised to minus n plus 1. And so when you differentiate this z with respect to x, 1 power of y raised to minus n plus 1 will decrease, and it will be same as saying 1 upon y raised to n. So you will get this term into, say, some dy by dx into some constant. Okay, and so this will be constant into dz by dx plus a of x into new dependent variable z, and this will remain unchanged, and that is going to be your new linear equation. So when I differentiate this dz by dx, we get the derivative of this 1 by y raised to n minus 1. That's actually same as y raised to 1 minus n. So 1 minus n into 1 by y raised to n. Derivative of this is y raised to minus n. So that is 1 by y raised to n into dy by dx. So which in turn give us that this term 1 by y raised to n dy by dx is same as 1 upon 1 minus n into dz by dx okay. So substituting this in 2, thus 2 reduces to this 2 reduces to 1 upon 1 minus n, the first term dz by dx plus a of x into z as it is equal to b of x. That remains unchanged. Now you can simply multiply throughout by this term 1 minus n, so that this become dz by dx plus 1 minus n into a of x into z is equal to 1 minus n into b of x. So this is linear equation of first order in z. So here we can find the value of z, and then you can substitute the value of z. That will give you the solution of the given equation 1. So this is how we solve the Bernoulli equation. This is how we reduce it to a linear equation and we solve it. Let's take one example. Example, solve first one, x square dy plus y into x plus y dx is equal to 0. Let me call this as equation 1. This is not at all in the required form. So let me try to put this in the form of dy by dx is equal to some function of x and y. So this is same as writing x square dy equal to minus xy plus minus y square into dx, and so you have dy by dx is equal to minus xy minus y square upon x square. And you can see that when you rewrite this, this is of the form dy by dx is equal to, from here, minus x by x square, that same as minus 1 by x into y, and from here minus y square, minus 1 by x square into y square. This can be again written as dy by dx plus 1 by x into y is equal to minus 1 by x square into y square. Now you can see that this is your Bernoulli form with the value of n is equal to 2. This is exactly of the form dy by dx plus some function into y is equal to some function of x into y raised to n being equal to 2. Now how do we solve this? We substitute here. Let me call this as equation 2. Substitute okay, so before substituting we will have to divide this. Divide 2 by y square, and so we get 1 by y square dy by dx plus 1 by x into 1 by y is equal to minus 1 by x square. So now we can substitute. I'll call this as equation 3. Substitute z is equal to 1 by y, and so that implies dz by dx is equal to minus 1 by y square into dy by dx. So that says that the first term is nothing but minus dz by dx, and thus 3 becomes minus dz by dx plus 1 by x into z is equal to minus 1 by x square. So this is the linear form, right? Still not linear form, you can just multiply by minus 1, but that's only a scalar that makes difference. So that's same as writing dz by dx is equal to minus 1 by x into z is equal to 1 by x square. That's a linear form. I'll call this as equation 4. So to find the solution of the given equation, we need to solve this 4. Now here in this case, we will observe the integrating factor. So a of x, first of all, we write it as minus 1 by x. If I compare it to a linear equation, b of x is 1 by x square. So the integrating factor is e raised to integral of a of x, that's into dx, that's same as e raised to integral of minus 1 by x dx, and that's same as e raised to minus log of x, and that's same as 1 by x. So thus the solution is given by, I'll directly write down. For this you'll have to refer to the previous lecture, that is lecture 5a, how do we get the solution using integrating factor of the linear equation. So the solution is given by, so the solution of 4 is given by integrating factor, that is 1 by x into z. Now here the dependent variable is z, so z is equal to integral of integrating factor into b of x. B of x is 1 by x square, 1 by x square dx plus c. So that's same as writing, that is same as writing 1 by x into z is equal to integral of 1 by x cube, that's same as minus x raised to minus 2 upon 2 plus c. And here I can now replace my z by, the value of z is equal to 1 by y, so this become 1 by xy is equal to minus 1 by 2x square plus c, and that's the solution to 1. So this is one example. Now let me take one more example which is slightly different from Bernoulli form, but we can adapt an idea of Bernoulli form to solve the same equation. Tan y dy by dx plus tan x is equal to cos y into cos square x. This is not a Bernoulli equation. This is not a Bernoulli equation as it is not in the prescribed form, but we can adapt an idea of solving a Bernoulli equation to solve this. See, this is of the form some function of y into dy by dx plus tan of x plus you have cos of y into cos square of x. So that's a function of y that is appearing over here. Now we will see what will happen if I divide this whole equation by the function of y that is appearing over here. So dividing 2 by cos y, we get tan of y upon cos of y dy by dx plus tan x upon 1 by cos of y is equal to cos square x. Now same equation can be written in terms of tan y. Okay, I'll write down this cos of y as sec of y dy by dx plus tan x into sec y is equal to cos square x. Now just look at this sec y. Now if I substitute the value of z to be equal to sec y, its derivative is nothing but sec y tan y into dy by dx, that is exactly appearing over here. And so everything will get converted into z plus tan of x dz by dx plus tan of x into z is equal to cos square of x, which is ultimately a linear equation, and then we can solve it using the working rule for the linear equation. So we substitute, let me call this as equation 3, substitute z is equal to sec y, and so dz by dx will be same as derivative of sec y, that is sec y tan y into dy by dx. So this whole term is appearing over here, and so we can replace it as it is. So thus I'll rewrite over here. Therefore equation 3 reduces to a linear equation dz by dx plus tan of x into z is equal to cos square x. This is a linear equation of first order in terms of z. So we are going to solve this for z, isn't it? Dz by dx plus some function of x tan x, z is equal to cos square. So here in this case a of x is tan of x, the coefficient of dependent variable, and the independent, b of x, that is independent of z, is cos square x. And so the solution integrating factor is given by e raised to integral of a of x dx, that same as e raised to integral of tan x. Integral of tan x is same as log of sec x, and so this become e raised to log of sec x. So this becomes sec of x. In fact, this is same as log of minus log of cos x, which can be written as log of cos x the whole raised to minus 1, that's same as log of sec x, and we have this as an integrating factor. So you need to multiply this integrating factor. So the solution is given by solution of 2 is given by, so in fact this is a solution to this equation, and which in turn a solution to the given equation. So I write down this as a solution of 2 given by integrating factor into, this is how I'll write down first the general formula, into z is equal to integrating factor into b of x plus c dx. That's same as writing sec x into z is equal to integral of sec x into b of x, that's same as cos square x dx plus c. So that's same as writing, the value of z, that is sec y, so you just substitute as sec y is equal to integral of this. This is same as sec x is same as 1 by cos, and so 1 cos gets cancelled, so integral of cos is same as sin x plus c. So that's a solution to 1. Thank you for watching this video, and have a nice day ahead.